So hi, in the previous semester I know you made an introduction to electromechanical energy conversion topics, but I would like to make a short review this week because we will be building AC motors on top of this knowledge. So probably the most useful equations is the force, okay, is equal to current density times B, or in other words it's the right hand rule where your thumb can show you the direction of the current and your fingers shows you the direction of the B, and your palm is showing you the direction of the force. So again, this is useful to find the force in a current carrying conductor in a magnetic field. You have seen there are some cases which we cannot use that equation directly. Actually, that Lorentz force is a specific application of the general electromechanical energy conversion equations. So again, if you just look at the PowerPoint slides or the web page, you can find some applications. There are some rail guns and homopolar motors, that kind of applications. All those things can be explained with the right hand rule. But again, if you recall your knowledge in the DC motors, like usual DC motor is a case where you have a B, okay, as a constant magnetic field, which can be created by some field windings, which can be excited like separately or connected in parallel shunt DC motors, that kind of things. Anyway, so you have some kind of magnetic fields, and here, okay, so you have like two coils, so it's like one like in a closed loop direction, so that is why, so that is coming like out of the page and that thing is going into the page. Actually, you can do the power calculations again, like your thumbs is like the current direction, so let's make for that one, okay, so it is coming out of the page, and then your fingers is the magnetic field direction, your palm shows you the direction of the force. So you can calculate, in this case the force is in this way, and here the direction of the current is reverse, so the force in this case is like that. So as a result, it will try to rotate that thing in the clockwise direction, right? So again, once it's moved, then it will pull back, so it will actually make some oscillations, and if there's any friction, it will stop some certain condition. But again, what we have in the DC motors, if you remember, once it goes over some degrees, there are some commutators in the rotor, and the direction of the armature coils reverse. So it is like a diode, not diode, but it's like a bridge diode, which inverses the AC, but you always switches the direction of the current, not using semiconductors like diodes, but mechanically using brushes. Anyway, so this thing can be explained by Lorentz force. But what about in this case? So here, let's say you have some current, okay, carrying some current, so you have some magnetic material, so this is magnetic material. Again, just to review some of the topics, so the relative permeability is much larger than 1, so for iron it is a couple of thousandths, okay, so it is more permeable than air. So again, if you just plot the direction of the flux, so you will see it is flowing in that direction, okay, so this is your B vectors. So again, if you just try to use the Lorentz force, okay, the problem here is in this item, so there's no J, okay, there's no J, but intuitively this is like an electromagnet, so once you excite that coil, it will try to close the gap. So basically, we will not be able to use the Lorentz force in that explanation. So that is why we have other set of equations, and those things can explain those cases as well as like that one. And this was using the magnetic energy, okay. So again, if you recall your lectures from the previous semester, by the way, I think you can still access the 361 course videos if you go to OT class and click the archive option, so you can still see the previous semester's videos. So if you have any questions, please have a look at the past year's videos of Emine Hoca's lectures and that kind of stuff. So anyway, so the main link, if you want to convert some electrical energy, okay, and if you would like to make some mechanical work, the interface between those two systems, in one side you have the electrical system. Again, don't think like as a circuit, but like as a system level. So in that system level you can have either flux and voltages, back EMFs, and also the currents. On the other side, on the mechanical system, what we have is the X is the displacement. Let me get myself smaller. Okay, that is the displacement, and this is the force. Again, so what we want to achieve, so at the end of the day, it is same for like wind turbines, electric cars, any industrial motors, like any small motors that you use. Either you are supplying electrical energy and getting some mechanical work done, which is the definition of the electric motor, or you can supply some mechanical energy, like in a wind turbine, for example, and you want to generate some electricity. So the interface between, there's no direct conversion between these two. How we convert between these two systems is through magnetic energy storage. Okay, so first we store the electrical energy as a magnetic energy, then the magnetic energy is converted to the mechanical energy. So we can write the electrical energy input, okay, assuming this is like working like a motor in this case. So the total energy input is equal to the mechanical work done plus the stored magnetic energy. So you can calculate the voltage, ampere, watts, you can calculate the joules, you can integrate the power, take the energy, and similarly you can calculate the joules, watt hours, kilowatt hours on that side. So the important thing is the unit of the magnetic energy is still joules or watt hours, watt seconds, whatever, or it's the same joules in the electrical system, it is the same joules in the mechanical system. Of course, in a more realistic system, what you have is you have some like resistive losses, okay, resistive losses, and again we have seen in the previous semester that there can be like eddy current losses or hysteresis losses, or in short, like let's take them like core losses, or let's call them magnetic losses. Okay, and again on the mechanical system you can have the friction losses and that kind of thing. So again, that affects like how much energy that you are giving and how much mechanical energy that you are getting. So those are the in some way those are the taxes that you have to pay, either if you are going that direction or if you are going that direction. So that is the main reason why we cannot have like 100% efficiency, or in the YouTube you can find like hundreds of different like erke dönergeci videos where they can generate infinite amount of energy. They can connect a motor to another generator and they say I obtained like infinite amount of energy. So unfortunately, those not real, and it is not possible all to those losses. Anyway, but for now let's ignore those losses and just have a look what happens purely at the electrical input, magnetic input, and mechanical energy output. So again, if you recall from last semester, we didn't use that term, but I would like to make a short introduction. So you can have, let me get rid of myself. So you can have like different graphs. So first one is, let's say you can have H and B, right? Again, your system can be linear, or in this case it can be non-linear, like that one, right? So let's say this is your operating system. So initially you were working at 0 magnetic field, and let's say you increased your operating temperature, let's say to 1 Tesla. Let me put those units. It is either Tesla, or you can write as like Weber per meter square. And the energy, okay, graphically, the energy that is stored in this system, actually again the unit of that one is, for BH graph, it is the energy density. I will explain that one. And this is joules per meter cube. All right, so this is the energy density. Again, let's go to a previous case. So for example, you can write the BH graph through here, and in the air gap you can define what is the B, what is the H, but that gives you the energy density at that point. Okay, if you want to get the total energy stored in that system, what you need to do is integrate it over the volume. Okay, so if you have let's say BH, okay, I will talk about the units, and if you integrate it over some volume, and again the unit wise it is joules per meter cube, and if you integrate that one, then you obtain the joules. Okay, or in other words, if you integrate B over some surface area, you get the flux. Let me do that. Either you can write that graph as, I don't know, let's say flux and current, okay, or flux versus MMF. MMF is, remember, number of turns times current. Number of turns is unitless, so this is can be written as ampere, and flux is Weber. Okay, so if you think that graph, let's say this is the same system. Okay, let me get rid of myself again. So if you think that you are operating that same system, so here that energy will give you joules. Okay, this is the energy. Actually, you can verify it. The first one, just thinking about the units. So this is Weber per meter square. This is Weber, right? And this one is ampere per meter H, and MMF is, you can write either like ampere turns. Again, the official unit for ampere turns, like turns, is unitless, so that is why we can write amperes. But let's use the ampere turns for that purpose. Then what you can do, okay, remember again this is a review, and if there are any points that is not clear to you, please go to your first semester lectures. The definition of the inductance, okay, what was the definition of the inductance? So it was the flux linkage per current, or it is like if you have n turns, okay, if you have n turns inductor, it can be written as like n times phi divided by current, right? So it can be written like that. So again, if I put that thing, so this will be flux linkage. So flux linkage, again, just to put it into perspective, it is Weber times turns. T is not time, turns. And here on the other side you can write it like current, which is ampere. So I just, from here to here the slope changes. I'm not putting it into scale, but we put the number of turns from MMF, ampere turns, to flux, so it becomes flux linkage, but the number of turns is unitless. So again, those areas are same, and again that gives you the energy. Okay, that is joule. And actually, if you think the slope, okay, slope of these curves, okay, what is the slope of flux divided by current? This gives you the inductance, right? So if that is a straight line, that means it is a linear system and your inductance stay constant, and if it starts saturating, that means it is inductance is reducing as it gets excited. Again, if you look at through that slope, remember B was equal to nu H, and that slope gives you the permeability. Okay, so if it saturates, then the permeability gets lower. Anyway, so long story short, if you look at here, so it can be either written as like B to H or flux linkage to current, and that area on the left hand side gives you the magnetic stored energy. Okay, so this is magnetic stored energy, and in order to do that, I mean, you can integrate those currents. So what you can do is integral of, let's say, current over the lambda from 0 to whatever operating point they are working on. Again, I mean, this is defined as like the energy, and that area is defined by co-energy. Again, that doesn't have a meaning as in the energy, but we will use, in some cases, use that area as a mathematical trick. And again, in a linear system, if this line is linear, energy is equal to co-energy. Those areas, two areas, are equal to each other. Anyway, so the magnetic energy stored in a system is that area. Okay, so you can again write here the same thing. The stored energy is from 0 to your flux linkage integral of current, or again from the BH curve. If you go to here, what you can integrate is you can get those areas integrated, and those tiny areas are dB, and that is where that equation is coming from. But the first integral gives you joules per meter cube energy density. Then you integrate, let me go to the previous video, so previous slide. So you can get it at one point, and you can integrate it over that air gap or over all the core to find the total stored magnetic energy. Okay, so that is important. And again, we know in linear systems from the graphical graphics that I showed you, the magnetic energy is equal to magnetic co-energy. Okay, and let me write it again here for simplicity. If this is current, this is your flux linkage. Again, that area, this is for linear systems. Okay, this is the energy, this is the co-energy. So the multiplication of the flux and current gives you the total area of that square or rectangular area. So that is energy, that is co-energy. And again, in a linear system, those areas are equal to each other. So if you divide that thing by 2, you can find the energy or co-energy. So only in like linear systems, what you can have is 1 over 2. Let me write it here again. So it is current, this is flux linkage. So that area, okay, is 1 over 2 flux linkage times current. And again, I know by definition, okay, the inductance is equal to flux linkage created per ampere. So instead of flux linkage, you can write L times I, and once you put that one, so that is the equation that you know very well. So the stored energy in an inductor, again, any magnetic circuit, even a straight line, or it doesn't have to be wrapped around a coil or something like that, even a straight line works as an inductor because it can create some magnetic field around it. So whenever you have some current, it will create some magnetic field. So even if it is really small, it will has some small inductance, and that inductance will store some energy, and the energy is like stored energy is in joules, like that. Or you can again, instead of current, you can write lambda divided by L. Sometimes that equation can be useful. Okay, so I think that is the most important slide of the lecture. Again, this is from photo from Highland Games in Scotland, where like really strong guys try to carry something from one distance to distance in the quickest time. Anyway, so my question is, let's say you have a stone like that. This guy is like Hercules and is carrying that stone. Why that stone is heavy? I mean, you can say because its mass is high. Yes, but its mass is not important, because in space that stone can be lifted, or in the moon it can be lifted really easily. It is heavy because we have, yes, mass, and also we have the gravitational field G. So the force that is exerting from that stone is like, you can say this is force is equal to m times g, right? Why it is m times g? Again, mass is like kilograms, that is important, and this is newtons, and all the mechanical systems, like we will use newtons. And again, if you multiply newtons with velocity meter per second, you can find the power. I mean, if you think about it, so that stone would like to go at a lower distance. I mean, I have that cup. Okay, hope this is green, so I'm using a green screen, so let's use that one. Okay, so let's say, I mean, I'm dropping it and it is falling down. Why? Because if you look at that way, that thing or that stone would like to minimize its potential energy. If it goes by some distance, okay, let's say delta x, it will lose some potential energy equal to mgh, or mg delta x. And what is the mechanical work done during that distance? It will exert some F, and it will exert some F time delta x. Again, that thing is joules, that thing is joules. Okay, again, this can be like really simple knowledge, but it is important if you can create the link with the magnetic systems. Again, you can get rid of delta x, and you can say F is equal to mg, which is like trivial, right? But if you think about it, the systems, I mean, all the systems tries to minimize their stored energy, like it's the entropy. So the same thing is happening in the magnetic systems. Whenever you have a magnetic system, they will try to minimize their energy, because you can have two magnets, like pulling themselves together. They want to attach together, because once they attach, they will, if you calculate it, they will reduce their magnetic energy. Or again, if you think about the previous system, like in that case, we couldn't explain it with the normal Lorentz force, but if you think about it, there is some energy in the system, and we will show once you excite it with the current, and it doesn't really matter the direction of the current, it will try to close the gap. The systems will always try to reduce their magnetic energy. And the same way that we did here, so if you take the derivative of the potential energy, it gives you the force. I mean, taking the derivative is basically moving it by a really small delta x when delta x goes to 0. That is the definition of the derivative. So we are moving it like really small distance, and we can calculate the mechanical force. So we will do the same thing for the magnetic system. Okay, so the derivative of the energy with respect to position gives you force here, and in the magnetic systems, we will take the derivative of the magnetic energy with respect to position, and it will show you how much force generated in that system. So this is, really, if you understand that thing, this semester will be quite easy, because the idea of all AC machines, all electromechanical systems lies on that fact. Okay, so what we are doing is we are taking the magnetic energy. So this is the stored magnetic energy, and it has to be a function of the x. So if the magnetic energy is not changing with respect to x, so it is as if like putting that stone on a horizontal line. And what is the horizontal force? I mean, horizontal force, if it is perfectly horizontal, there will be no force in the horizontal direction, because if you move delta x in that direction, there will be no change in the potential energy. So it is the same with the magnetic systems. If there is no change with respect to position, then there will be no force. Again, that's why we are taking the derivative. And again, we are keeping our flux constant, because it will not be like a fair comparison if you just increase the current during that instance, because you are supplying more electrical energy. Why there is a negative there? That is, the convention, because if you think about again with that one, that stone tries to reduce its potential energy. So if it is going down, the derivative of the potential energy is negative. And if you define that force direction as positive, because if that is creating some force, the derivative comes negative. So you multiply it with some negative direction. So the positive directions show the positive sign shows the direction of the force. So that is, why we have some negatives. So once that if it is reducing in the x direction, the derivative will be negative. So negative, we will create some positive force. Again, I advise you to have a look at those lectures. Those video lectures are, just to be a guideline for you. I, strongly advise you to go through your textbooks or extra links like that, and I want you to make the derivations yourselves. Okay. So again, if you put all those things, again, what we obtained like from the previous slides is like lambda square over 2Lx, or you can use the other one. Again, you can get confused what happens like if I use 1 over 2 Li square. Actually, be careful about the co-energy, because with the co-energy there will not be any negative sign. But again, you don't have to worry about those things. We will not be using like much of that equation, but the useful term, again, I think Emin Hoca derived those things in the first semester. The force, okay, is generated in the direction of the inductance change, or let me put it that way, if there's a change of inductance with respect to position, then there will be force. Okay, so that is why, for example, I think if you think of a rail gun, okay, again I put some slides. Okay, so let's say there's a rail gun here, so there's some current going out, there's some current flowing through here, and it is creating some B in that direction. Okay, so there's some B. I hope the direction of the B is correct, but anyways, so you can both use the Lorentz force. There's some current carrying conductor in a magnetic field. If you calculate it, you will find that thing is creating some force here, and also the rails would like to go in that direction, but they are fixed and they cannot move, so only that trajectory moves. So that case can be explained with the Lorentz force, but it can also be explained using that term, because the systems will try to maximize, that is again important, all magnetic systems try to magnetic systems tries to maximize their inductances or minimize the reluctance. Again, L is equal to N squared over R, so that they are inversely proportional. So if that armature moves like in that way, okay, then you can argue for the inductance definition, it is flux linkage divided by current, or you can say the number of turns is 1, so you can say flux divided by I, or it is B times area divided by I. Area is that area. So you can see as the armature, that moving trajectory moves from that position to that position, its inductance increased. Okay, so inductance increased, so it is proportional with that one. So that way, the system tries to maximize its inductance, so it will move in that direction. The interesting thing, another interesting point is it is proportional with the square of the current. So it has two consequences. So if it is a linear system, the current value has direct effect on the force. If you can double your current, the force will increase 4 times. Okay, so that is the first direct effect. So the current is really important. And secondly, because of the current, have a look at that one, the direction is always, in that one, that term is always positive. So that means even if like cancel that current and apply, let me use a different color, let me use a opposite current, so I reverse the direction of the current, so that armature will not move in the opposite direction, because still, even if the current is like applying in the negative case, the direction that increases the inductance is still that way. Or you can see it even if I put some negative current to that value, so once you take the square, it will end up in the positive term. So the thing that defines the direction of the force is the derivative of the inductance. So the armature in this case, or it can be the rotor, whatever, they will move in the direction that maximize the inductance, or they will move in the direction that minimize the reluctance. Okay, so again, if you just go back to here, so for this case, we can say regardless of the current direction, you can give positive current, negative current, you can give AC current, that device will always pull towards that coil, because remember, the reluctance is length of that one. Okay, and as you reduce the length, the reluctance will get smaller, and the inductance, let me put it here, overlap. So L is equal to N squared divided by reluctance, so they are inversely proportional. So as you move the straight item closer to C-shaped item, the length reduces. As the length reduces, the inductance increases, so it will move in the direction that minimizes the reluctance, and that's minimizing the reluctance and increasing the inductance. Okay, so those terms are important in that way. So again, it is the same, so you can actually define the characteristics of the inductance in any systems. Again, this is the main principle of all AC motors, so we will use those two equations quite a lot. Okay, again, let me show you some applications. There are some videos, but I would like I don't have time to show those things, but please click on the links and also reading materials, YouTube videos, and there are some interesting applications. The first one, probably everyone probably are listening this video using a speaker, and they are kind of simple, right? So you can think it is just a basic solenoid, but actually it is more complex than that. Actually, in the web page I have an animation showing that one. And what you have here, of course, you know that one. So here probably this is the magnet. There's a magnet here, and inside that thing there's a coil, and depending on the amount of the current that you are giving, it creates some force. So it is moving that speaker, back and forth, and that thing is pushing the air, and that air pressure actually creates the sound, and we hear it. Okay, so it is simple, but if you think about it, how the force is generated, and there's like some frequency response of the coil, so it is a highly nonlinear system. So the same amount of, so at the end of day, so that is like an inductance, right? Yes, it is j omega L, the coil itself. There's also some resistance to it, so it is R plus j omega L. So there's some kind of a frequency response. So that is why, if you get some bass speakers, so they are specialized for low frequencies waveforms, right? So it's there like boom, boom, boom. Or there are some special speakers that gives like more high frequency sounds. They are usually like has a smaller diameter and that kind of stuff. But at the end of the day, it is all an electromechanical system, and you have an analog signal, which is the sound signal, and you want to generate the force. And in that nonlinear system, you want to generate as much as linear response that you want. Okay, so I don't know if you know this guy. So this was a professor in MIT, electrical engineering, and actually I think like 5-6 years ago or maybe more, I think he passed away. And the name of this guy was Amar Bose, and he was the founder of the Bose corporate company. As you know it, Bose speakers are like really expensive, high-end speakers, because in the like 50s and 60s, what Amar Bose did, like the modeled all those coils, all that nonlinear system, modeled how much force is generated in that nonlinear system, and try to get the best sound characteristics by linearizing that system. So actually he founded his company on his knowledge on the electromechanical energy conversion. Then they keep building a really nice equipment. And actually, after he passed away, I think he gave away all his shares in the Bose company to MIT. So as far as I know now, MIT is the majority shareholder in the Bose Corporation. So whenever if you buy a Bose speaker, you are making some donation to MIT as well. Okay, there are some also, it doesn't always like motors or rail guns or that kind of things. There are also some other applications, like one of them is like the malaria. Again, nowadays we are too busy with the coronavirus, but actually malaria, sıtma, it is quite a deadly disease as well, especially in poor countries. And every day, if you have maybe that numbers even increased, it's more than like 3,000 kids, and actually it affects, I think, younger people more. Anyway, the idea thing is there's a virus carried by a special type of mosquito, and once you get infected, actually it affects your blood cells, okay, red blood cells. So they are carrying the oxygen. So actually your red blood cells starts disintegrating. I mean, your body is building new red blood cells, but again, I think the virus damages them at a faster rate that your body can build new ones. So that is why, I mean, a stereotypical things like having malaria, they die like feeling really cold and that kind of things, because they are feeling really cold because their red blood cells are damaged. So your body cannot get enough oxygen and cannot generate enough energy for your body. So that is why you are feeling cold once you have the malaria. And the interesting thing is the diagnosis method, previously what they used to do is they get a blood sample and someone is like counting on the microscope the number of red blood cells that you have, and it is a tedious process and it takes quite a lot of time. And what they propose, if you remember from your biology lectures, is those red blood cells have some iron material in it, right? Hemoglobin, and that's the iron actually attached to the oxygen, and that is how the oxygen is carried to your cells. And because of that extra, damaged blood cells, the iron content in your blood increases. So iron has a higher permeability. So this is a really recent technique, by the way, maybe like 4 or 5 years old. So what they propose is, so you have your damaged red blood cells, okay, so they are applying, there's no B field here, and once they apply a B field, all those molecules, like iron carrying molecules, align themselves with the B because they are moving to the minimum reluctance position. So all of them are aligned, and once they are all aligned, you can send some light and you can measure how much light is produced on the other end. So suddenly there are some automated malaria detection kits where you can drop a blood and you apply a small magnetic field and you measure how the light is transparency to light under magnetic field, and it will give you if the patient has some malaria or not. And again, I think they also use the same technique to filter out the infected red blood cells by applying some magnetic field, and you can click those links. So again, what I want to show you is like that idea, the link between magnetic field and the mechanical systems can have like really nice applications in the field. So this is, I think, the PhD student who came up with the idea. Please have a look at the reading materials. Okay, so just to summarize again, please have a look at the last year courses on the magnetic circuits and that kind of things. So magnetic systems tries to maximize the inductance and minimize the reluctance. Okay, so that's for now, and we will move on the rotational systems in the next video.